Okay. Any questions on this density matrix thing?
In the grand canonical ensemble in the book, they said that it should be this operator should commute also with the number operator.
Mm-hmm.
Which is something I did not get. I can get why it should commute with H because when we try to use the commutator relationship, we used Schrödinger wave equation, which has a relationship with time derivative, and from there we went on. But there is no equivalence of Schrödinger equation with derivation with respect to the number. It was something so mathematically it has no justification. So why should it compute with the number?
Okay. Before answering your question, let me ask you another question. What do you remember about the Schrödinger picture?
The states should be time dependent and operators should be time independent.
Schrödinger picture. States are time dependent. Psi is time dependent. And operators time independent.
Heisenberg picture is the other way around.
Heisenberg picture. Time independent. And the operators are time dependent. Let me add the third line. What about rho? Rho is an operator, right? In the Schrödinger picture, is rho time dependent or time independent? But you see, rho is constructed using the states. But in Schrödinger picture, states are time dependent.
For instance, the eigenstates of an operator. If you consider an eigenstate of operator, it will not change in time. If you construct matrix with the eigenstates of an operator.
Well, let me ask you this question then. Whether you are in time Schrödinger picture or Heisenberg picture,
Expectation value should give you the same result.
at a given time t, the density matrix will be, if you want to construct the density matrix at a given time t, what you do is you just take the wave functions at that time and the probabilities at that time and construct your density matrix. So I would say that in the Schrödinger picture, rho is time dependent.
But if I took psi and psi prime to be given in terms of psi 0 and psi 0, I would reach to each psi t using a time evolution operator, but the effect of these two should cancel each other since it would be of the form of I to the e to the iht. So their multiplication should cancel and I should get a time independent, right?
What do you mean? Can you repeat again?
If I took psi to be equal e to the iht, the time evolution operator, times some initial state.
Is each power I over ht psi 0, okay.
So the Hermitian conjugate should be iht, and when I multiply, the effect should cancel each other.
Well, let's see. So you are multiplying psi, the ket psi and the bra psi. Well, the ket psi is this one. And the bra psi is this one. How do they cancel?
If I'm applying this on, should apply in a way where h collapses to an eigenvalue more than a. But even if I moved it that way, if t is the same,
Well, I cannot. There are operators between those two exponentials. So that exponential does not necessarily commute with that operator. But let's also go back. You said that whichever picture you use, the expectation value should be independent. Okay. The operators expectation values of operators can be time dependent. There is nothing wrong with that. But that time dependence in the Heisenberg picture is in the operator itself, right? The operator changes with time. In the Schrödinger picture, the operator is time independent. So rho should be time dependent in the Schrödinger picture so that you have a time dependent expectation values.
So in these two traces, you kept the probabilities time independent, right?
Yes.
Okay. They're constant. You can also, can you change, for example, thinking Schrödinger picture, can you say pi is a function of t and psi's are diagonal states of the operator?
Well, it depends on what kind of a system you have. If you have an isolated system, I would say that no. PIs you cannot change. Of course, by the way, this thing over here, you can write as psi I, psi, it will probably be j. 0 at t equal to 0, but then you will get Pij at the time t. Those are the same thing. But if you create your system and you have certain probability that it will be in the state psi I, at the time t, you will have the same probability for the system to be in the state psi I of t. It doesn't mean that it has the probability pi that it will be in the state psi I. Because psi I t will be in general a superposition of many different states. So of course you can write your, this is essentially a means of, a problem of choosing the basis which you will use to write down the density matrix. The density matrix can look quite different in different bases. And using that freedom, I can always move the time dependence to the PIs, but in that case, in that basis, the density matrix will not be diagonal in general. But if I know the psi I and the pi at some t equal to 0, I can use the same pi to write down the density matrix. The thing I have to pay attention to is that the states I need to use are not psi i's anymore, they are psi i's at the time t, whatever they are.
Psi i's at time t could be superpositions of all the psi i's.
In general, you see, all the psi I and even more. You see, psi I need not be a basis. They can be anything. You see, for example, you can say that you can create such a system that half of the particles, half of the spins are in z plus, and the other half in x plus. These are not orthogonal to each other. So then let's write the example. You see, the density matrix corresponding to this state will be 1/2 z plus, and 1/2 x plus, x plus. Z plus and x plus, they don't form they form a non-orthogonal basis, if you like. I can still express everything in terms of z plus and x plus, but they won't be orthogonal to each other. What is x plus? In the basis z plus and z minus. Okay, some basic quantum mechanics. 1 over square root of 2. This is my x plus basis. So the density matrix is 1 over 2 z plus plus 1 over 4 z plus z minus z plus z minus. Let me multiply them out. You see, in the z plus, I have 1 over 2 and here I have this product. From that product I have 1 over 4. Then I have z plus, z minus with a coefficient 1 over 4. It's only this product. Then I have the cross terms, z plus z minus plus z minus z plus. Sorry. And both of them have coefficients 1 over 4. I can write this as a matrix. Well, 1 over 2 plus 1 over 4 is 3 over 4. Z minus is 1 over 4. This is 1 over 4. This is 1 over 4. What is the trace of rho? It's 1. It's the total probabilities. Well, let's calculate rho squared. Let me just write another one of them. Well, the 1 element will be 10 over 16. The 1 2 element will be 4 over 16. This will be 4 over 16. And this will be 2 over 16. What is trace of rho squared? 12 over 16 or 3 over 4, which is less than 1, which tells me that it's a mixed state. You see, if trace of rho squared is 1, it's a pure state. If it is less than 1, it's a mixed state. You see, a pure state, when you diagonalize, when you diagonalize the density matrix, a pure state will have 1 in one of the entries and 0 everywhere else. So a square is actually itself. And square is also the trace, the square also has the trace 1. If it's not a mixed state, when you diagonalize it, there will be 2 entries at least along the diagonal, each one being less than 1. So square of those entries will be smaller than the entries themselves. So if you just sum numbers whose sum is 1, if you sum smaller numbers, you get something less than 1. So that's one of the checks that you can do, whether a given state is a mixed state or not. Okay, how do we calculate the average average spin in the z direction for this system? Well, we said that is nothing but the trace of Sz times rho. Sz is h bar over 2, 1 minus 1, 0, 0 for spin 1/2 particles. Rho we had just calculated, it's that one. It's 1 over 4. That's common in everything. 3, 1, 1, 1. 3, 1, 1, 1. Well, let's go ahead. This is h bar over 8. Trace of, this entry is 3. This entry is minus 1. I don't really care about what these entries are. This is h bar over 4. This is the average spin in the z direction. Average spin in the x direction. This is trace Sx rho, which is, do you remember what Sx is? 0110 and rho 3111 h bar over 8 trace of, well, again, it's enough to calculate the diagonal entries. This is 1, this one is also 1, this is also h bar over 4. You see, when we are talking about the states in defining the density matrix, like in this example, they don't need to be orthogonal. They don't need to be complete. And still it is a well-defined quantity. Of course, if you want to write rho as a matrix, well, it will be wiser to choose an orthogonal basis. In this case, I just chose the bases z plus and z minus. Yes, question? Okay. Sure.
It was mentioned above that the time derivative of rho at equilibrium should be 0.
Mm-hmm.
And this, and according to that rho must depend explicitly on Hamiltonian.
So, by the way, we still have his question, but okay. So, no, I mean, you see, that was probably part of, okay, what we have shown is derivative of rho with respect to time was with a certain commutator of h and rho. And in equilibrium, this has to be 0. You see, here we define rho for an arbitrary system. It doesn't have to, we didn't define a temperature, it's just not an equilibrium system, anything. You can define rho for anything. Now, if you are looking at equilibrium, the expectation values will not depend on time. So if rho is explicitly depending on time, then your system will be changing with time. But that's not how we define the equilibrium. I mean, one necessary property of equilibrium is that your system should not be changing in time. So time derivative of rho should be 0. Then the question is, you see, it's not exactly correct to say that rho depends only on h. Whatever is conserved, in fact, rho, this tells me that rho should be a function of whatever commutes with the Hamiltonian. Hamiltonian commutes with the Hamiltonian. If the total number of particles commutes with the Hamiltonian, then rho can be a function of the number of particles. If rho commutes with the momentum operator, then rho is a function of the momentum operator. Can be a function of the momentum operator. If angular momentum commutes with the Hamiltonian, then rho can be a function of the angular momentum operator. Not necessarily just the h. Now, of course, we can always go to a system in which the total momentum is 0. Well, the different parts of a system in equilibrium cannot have different momenta. So either everything is translated in harmony, there cannot be relative motion, there cannot be relative rotation. So the whole system, you see, if this is in equilibrium, if I translate it, this is still in equilibrium. But if different parts of the system has different momenta, then it won't be in equilibrium. I can always go to a reference frame in which this is at rest, and I can always go to a reference frame in which this is not rotating. Of course, it won't be an inertial reference frame, but I can always treat my system in a non-inertial reference frame by just adding a suitable potential to my Hamiltonian. So I can always make sure that P is 0, L is 0. So rho will be a function of, in general, the Hamiltonian and the number of particles. Now, in the case of the microcanonical and the canonical, the number of particles is fixed. So, I mean, you don't even need to mention the number operator. It will give a fixed number. In the case of the grand canonical ensemble, you have actually shown in the book, it shows that rho is actually proportional to e to power minus beta h minus mu times n. Now, does rho have to depend on, does rho need to commute with n? Or does, I mean, was it rho commutes with n or h commutes with n?
Rho commutes with n.
Okay, why should rho commute with n? Should it?
Because at equilibrium, total derivative should be zero.
So, well, that only tells me that it's highly probable that rho is a function of the Hamiltonian, because rho commutes with the Hamiltonian. But why should rho commute with n? Well, in fact, depends. If h commutes with n, rho commutes with n. If h doesn't commute with n, rho doesn't commute with n. You see, even from here, you see that if h doesn't commute with n, then rho doesn't commute with n. But then we will have problems. How do you treat a system using this treatment in which h and n does not commute with each other? You cannot talk about a definite number of particles if the system has a definite energy. Or if the system has a definite number of particles, then you cannot have definite energy. It doesn't have to commute with n, rho. But in most practical cases, h will commute with n. For example, in fact, we have a system in which h doesn't commute with n. Electromagnetic fields. H changes the number of photons. So h doesn't commute with the number of photons in my system. But in that case, it's not a problem. In that case, mu is 0. Then we say, since the number of particles is not conserved, then we just set n equal to 0. Mu is equal to 0, sorry. Remember, why did we introduce this constant mu in the ensemble theory? We just wanted to fix the average number of particles, independent of other properties of the system. I just introduced mu as a Lagrange multiplier to conserve the number of particles. If there is no conservation of the number of particles, there is no mu. But if the number of particles is conserved, that means h commutes with n. So rho commutes with n. Now let's go over the derivation of the density matrix for a two-particle system. if you like. You see, one lesson of this whole chapter is that rho in equilibrium is actually just rho n, where n is an energy eigenstate. So in the energy basis, in equilibrium, the density matrix is diagonal. And this rho, if we are doing canonical ensemble for, let's say, non-relativistic particles, this will be just e to power minus beta En. And well, it's not necessarily non-relativistic for the time being. Now, okay, this is the density matrix. You can just look at any of its matrix elements. What are the diagonal elements of the density matrix? Let's say rho, R1, R2. Well, this R1, R2 basically tells me that one of the particles is at the point R1, the other particle is at the point R2. What is this diagonal element? Now let's go back to the initial definition, in fact. Well, this is how we define rho. Well, let's look at the diagonal element. This is just I, pi, well, psi I n squared. What is this? Well, n can be arbitrary, it can be position, it can be energy, whatever you like. Well, that is the probability that the state psi, if the particle is in the state psi I, that is the probability that it will be in the state n. Okay. Well, of course, the particle is not necessarily in the state psi I, so there is a probability that it will be in the state psi I. Then we multiply it with the probability that if the particle is in the state psi I, the probability that it is in the state n. And then sum over all the states psi I. This is nothing but the probability the system is in state n. For example, if you want to calculate the probability that, I don't know, Zeynep is in that seat, what you do is you first calculate the probability that Zeynep will be in the classroom. And given that she is in the classroom, you multiply it with the probability that she is in that seat. Basically the same idea. So this is the probability. Well, in this case, since R1 and R2, they are continuous variables, it will be the probability density. Well, then what is, for the given system, R1, R2, R1, R2, this will be e to power minus beta. Well, what are the energies? The momentum of the first one squared divided by twice m plus momentum of the second one squared divided by twice m. Of course, there is a 1 over z. 1 over the normalization. Let me write Q. And then we have a R1, R2, and well, this n are given by P1 and P2. P1, P2. R1, R2. Or 1 over Q. Now the states of the particles will be labeled by P1 and P2. E to the power minus beta, P1 squared over 2m plus P2 squared over 2m, R1, R2, P1, P2. Squared. Now what is this, that matrix element? They're just products of plane waves. I have two particles, one with momentum P1, the other with momentum P2. So it will be e to the power I, P1 times R1, e to the power I, P2 times R2. But these are identical particles. Since they are identical particles, well, the particle that has the momentum P1 can be the other one. So I have P1 times R2, e to the power I, P2 times R1. And these two components should have the same probabilities. So this is the wave function. Under the exchange of particles, the wave function should at most get a minus sign. So I can either have a plus sign in between or a minus sign in between. And then there is a normalization of this wave function. Well, then the rest, I mean, I will not continue, but you see, you know the wave functions. You have the Gaussians over here. It's just the summation over the momenta, but you should just convert them to integrations over the momenta. And then you calculate this density matrix. Rho 2, the density for two particles, R1 and R2. This just gives you the probability that you have one particle in position R1, the other particle in position R2. And okay, the details of the derivation are in the book. You'll see that if you get the minus sign as a function of R1 minus R2, this probability just goes to 0. No, it doesn't go, I think it doesn't go to 0, but it diminishes as the particles R1 and R2, R1 goes to R2. And it is enhanced if R1 goes to R2. You see, there are no interactions between the particles. These are just free particles. But even though they are free particles, the probability of them to be at the same point is 0 if they are fermions, and it is enhanced if they are bosons. So we often say that the fermions avoid each other and the bosons, they try to be together. But keep in mind, there are no forces here. They are not exerting any forces to each other. They are non-interacting particles. Okay, any last minute questions? I said, the rest is just technical computations and integrations. What is important is what you get from the result. Okay, so we will continue on Wednesday.